The Cretaceous ocean left behind evidence that, even now, 66 million years later, is difficult to look at without feeling something. A shark's tooth still embedded in the backbone of a flying reptile. Not beside it, not beneath it, inside it, locked in bone exactly where it landed, preserved across 66 million years as evidence of a single moment in an ocean where almost nothing was safe from anything else. In some regions, the surface waters reached 35 degrees Celsius, which is about 95 degrees Fahrenheit. The seas were warm enough to hold less oxygen, creating vast dead zones that persisted for hundreds of thousands of years. Sea levels stood as much as 200 meters, which is about 656 feet, higher than they do today. The oceans swallowed the continents, spreading inland and carrying their predators with them. A land lizard no bigger than today's Komodo dragon entered those waters and, in less than 25 million years, became an ocean predator nearly 57 feet, that is, nearly 17 meters long, one of the fastest complete marine transformations ever recorded. The fossil record shows predators swallowing other predators, sharks attacking flying reptiles, giant fish dying with sharks still undigested inside their stomachs, mosasaurs hunting almost anything that shared their water, including one another. These are not artistic reconstructions. The bones exist, the bite marks exist, the stomach contents exist, the tooth is still in the vertebra. In today's story, we're diving into one of the most dangerous oceans our planet has ever created. Across nearly 80 million years, the Cretaceous became one of the longest chapters in Earth's history. It began about 145 million years ago and reached its conclusion about 66 million years ago, a span more than 15 times longer than modern humans have existed. Such immense stretches of time allowed landscapes, climates, and entire ecosystems to change with remarkable persistence. Nothing in this world remained hurried. Every transformation accumulated across millions of generations until the planet itself operated under conditions unlike those of today. One of the greatest differences appeared at the poles. Permanent ice had vanished, leaving no frozen caps to lock away enormous volumes of water. As the oceans expanded, sea levels climbed as much as 200 meters, which is about 656 feet. Coastlines dissolved into broad inland seas that covered regions now occupied by forests, farms, deserts, and cities. Places that today lie hundreds of kilometers from the nearest shore, which is about hundreds of miles inland, once rested beneath warm marine water where sunlight reached the seafloor across immense continental shelves. The atmosphere carried far more carbon dioxide than it does today, reaching roughly 2,000 parts per million, almost 5 times modern levels. That abundance trapped additional heat across the globe, raising average temperatures by approximately 5 to 10 degrees Celsius, or about 41 to 50 degrees Fahrenheit, above those of the present world. Even the highest latitudes escaped prolonged freezing. Forests spread across lands now associated with snow and ice, while fossil discoveries reveal palm trees and reptiles living within the Arctic Circle, reminders of climates that would appear almost impossible to modern eyes. Warm oceans behave differently from cooler ones. Heat reduced the amount of dissolved oxygen the water could retain, altering marine habitats from the surface downward. At the same time, flooded continents created immense shallow seas where sunlight reached broad expanses of the seabed. Nutrients circulated through these waters with exceptional efficiency, supporting blooms of microscopic life that formed the foundation of an extraordinarily productive food web. Every layer became crowded with organisms feeding, reproducing, and competing across habitats that stretched almost without interruption around the globe. These conditions rewarded body plans able to exploit abundant prey. Populations expanded across connected seas instead of remaining isolated by narrow coastlines or enclosed basins. Species encountered new competitors, new hunting grounds, and fresh opportunities with unusual frequency. Evolution responded through gradual changes that accumulated generation after generation, producing larger bodies, greater diversity, and increasingly specialized ways of hunting. The ocean itself encouraged experimentation on a planetary scale, offering room for countless lineages to flourish at the same time. Each physical ingredient strengthened the next. High seas created habitat, warmth accelerated biological activity, abundant food supported growing populations, and uninterrupted marine corridors allowed successful predators to spread across nearly every shoreline. Together, they formed an environment unlike any modern ocean, one prepared to sustain creatures whose size, reach, and influence still astonish paleontologists studying their remains today. Within this remarkable setting, new rulers were already beginning to emerge from directions almost no living observer could have anticipated. For far longer than the reign of any predator that would come afterward, another lineage already commanded the open sea. Ichthyosaurs had entered the oceans roughly 150 million years before the closing chapter of the Cretaceous. Their bodies carried the familiar outline of dolphins, although they were marine reptiles shaped by an entirely different evolutionary journey. Streamlined forms, powerful tails, and large eyes allowed them to pursue prey across nearly every ocean on Earth. Fossils recovered from many continents reveal how widely they spread, becoming the established hunters of marine ecosystems through an interval of time almost impossible to comprehend. Generations succeeded one another across millions of years with remarkable continuity. Large species occupied the highest levels of the food web, while smaller relatives filled other hunting roles beneath them. Some evidence suggests elevated metabolisms that may have allowed sustained activity in cooler waters, extending their reach into environments unavailable to many other reptiles. Their success appeared so complete that the ocean seemed permanently organized around their presence, as though the position they occupied had become a permanent feature of Earth's marine life. Then the record changes. Around 100 million years ago, ichthyosaurs disappear. Their disappearance arrived well before the asteroid that would later end the age of dinosaurs, leaving paleontologists to examine a mystery preserved across scattered layers of stone. Several explanations remain under active study. Gradual climate shifts may have altered the distribution of prey. Rising ocean temperatures could have transformed habitats faster than these specialists could adapt. Changes within marine food webs may have reduced the abundance of the animals they depended upon. More than one influence may have worked together, each adding pressure until recovery became impossible. Their absence left something extraordinary behind. The highest hunting role across the world's oceans no longer belonged to anyone. In the warm, productive seas that had spread across flooded continents, the greatest ecological opportunity of the age stood open. Every abundant prey population, every newly connected coastline, and every expanding marine habitat existed without a dominant ruler capable of controlling them on a global scale. Such vacancies rarely remain empty for long when resources continue to multiply. Evolution does not plan ahead, yet living populations constantly explore new possibilities through countless small variations passed from one generation to the next. When an opening appears, those variations can suddenly become valuable. Features that once offered only modest advantages begin shaping entirely new ways of life. Across geological time, an empty ecological niche becomes an invitation written into the landscape itself, rewarding whichever lineage can answer it most effectively. Along the margins of those expanding seas, the future contender gave little indication of what it would eventually become. It still moved across solid ground with limbs suited for walking. Its body belonged to a predatory lizard, comfortable near shorelines where land and water met. Nothing in its appearance suggested that its descendants would one day replace the vanished rulers of the oceans. Even so, the conditions had already aligned. Vacancy existed, the world remained rich with opportunity, and the first steps toward an entirely new dynasty had already begun, carried forward one generation at a time. The shoreline became the meeting place between two worlds. Waves reached across the sand while large hunting lizards searched the edge where fish, shellfish, and stranded animals gathered with every tide. They still belonged to the land, carrying sturdy legs, broad feet, and lungs adapted for long hours above the surface. Their appearance would have reminded a modern observer of the Komodo dragon, powerful reptiles capable of entering shallow water whenever opportunity appeared, yet still rooted in a terrestrial way of life. Around 98 million years ago, the fossil record begins revealing something different. The earliest true mosasaurs emerge with bodies already showing unmistakable signs of change. Their ancestors had crossed an evolutionary threshold that few vertebrates have ever approached. Generation after generation, natural selection favored individuals spending more time in coastal waters, where abundant prey rewarded every improvement in swimming ability. Small advantages accumulated gradually until an entirely new form of life began taking shape. Across less than 25 million years, one of the fastest complete marine transformations known among vertebrates unfolded. Limbs broadened into flippers that generated efficient thrust instead of supporting weight on land. The body lengthened into a streamlined profile that reduced resistance while moving through water. Muscles shifted toward powerful side to side motion, and the tail developed a crescent shaped fluke resembling that of fast swimming sharks. Every major change complemented the others, producing an animal designed for speed, endurance, and control in open seas. Perhaps the greatest transformation involved reproduction. Early members of this lineage still depended upon land through their ancestors, yet later mosasaurs abandoned that connection entirely. They became viviparous, meaning they gave birth to fully developed live young instead of laying eggs. Newborn animals entered the ocean immediately after birth, already surrounded by the environment that would sustain or challenge them throughout life. Shorelines no longer served as nurseries, and every generation began within the water itself, completing the final separation from their terrestrial origins. 25 million years may appear almost unimaginably long on a human timescale. Geologically, it represents a remarkably brief interval. It is roughly comparable to the span since the earliest members of the dog family first appeared. During that same amount of time, a coastal hunting lizard evolved into an ocean predator reaching about 57 feet, that is nearly 17 meters in length. Descendants of those first shoreline reptiles eventually occupied marine habitats around nearly every continent, including Antarctica, demonstrating how rapidly evolution can reshape an adaptable body when conditions strongly favor change. The family connections remained visible despite this extraordinary transformation. Mosasaurs belonged to the same broader reptile group as modern monitor lizards and snakes. Living relatives still carry echoes of that ancestry in flexible skulls, elongated bodies, and specialized jaws. A visitor walking through a modern zoological park could stand before those familiar reptiles without immediately recognizing the distant relationship. Geological time, working through countless generations, expanded that shared blueprint into one of the greatest marine predators the planet has ever known, while preserving subtle traces of its beginning within every remarkable adaptation. An empire is rarely built by a single ruler. Across the Cretaceous seas, the success of mosasaurs came from diversity as much as size. They formed an entire dynasty composed of dozens of species living at the same time, each occupying a different place within the ocean. Some measured only about 3 feet, which is about 1 meter in length, while the largest stretched to 57 feet, that is nearly 17 meters. Together, they filled nearly every hunting opportunity available, creating one of the most varied groups of marine predators the planet has ever known. Among them stood Mosasaurus hoffmanni, the largest confirmed representative of the family. Adults reached approximately 57 feet, that is, nearly 17 meters, and weighed close to 4 tons. Their length exceeded that of a modern school bus, while their weight surpassed that of an African elephant. Their skull carried an unusual design. The lower jaws could flex slightly, allowing larger prey to pass deeper into the mouth without becoming trapped. Along the roof of the mouth lay a second row of teeth, known as pterygoid teeth. Once prey crossed those backward-pointing teeth, escape became extraordinarily difficult because every movement carried it farther inward. Another branch of the family followed a different design. Tylosaurus grew to around 40 feet, that is nearly 12 meters, and possessed a long, solid snout, unlike that of its relatives. Paleontologists believe this reinforced structure functioned as more than a simple extension of the skull. Powerful forward strikes may have stunned prey before the jaws closed, allowing the animal to combine momentum with biting force. The skull itself became part of the hunting strategy, adding another method to the growing collection of adaptations appearing across the dynasty. Smaller forms developed different strengths. Platecarpus lacked the immense size of its larger relatives, yet its streamlined proportions suggest an agile swimmer capable of rapid pursuit through open water. Fossil evidence indicates a style of hunting based upon speed, maneuverability, and repeated chases instead of overwhelming force. In several respects, its behavior may have resembled that of modern orcas, although it evolved through an entirely separate lineage and under very different environmental conditions. The variety extended beyond differences in size and hunting style. Chemical signatures preserved within fossilized teeth reveal that some mosasaur species spent prolonged periods in fresh water. This technique, called isotopic analysis, examines naturally occurring chemical patterns locked inside growing teeth. Those patterns preserve details about the environments where the animals lived while the teeth were forming. The evidence indicates that certain mosasaurs traveled into rivers far from the open ocean, expanding their range beyond coastal seas and demonstrating a flexibility uncommon among large marine predators. Viewed together, the family resembles an entire marine community rather than a single type of reptile. Different body shapes specialized for pursuit across open water, ambush within shallower habitats, feeding near the seafloor, exploration of river systems, and even capturing prey approaching the surface from above. Instead of competing for exactly the same resources, they divided the ocean into overlapping territories where each form excelled. Their combined presence reached from the seabed to the sunlit surface, leaving remarkably few places beyond the influence of at least one member of this remarkable dynasty. Before the largest mosasaurs came to dominate the seas, another hunter already moved through those waters with remarkable confidence. Its name was Cretoxorhina mantelli, although many paleontologists later gave it a memorable nickname, the Ginsu shark, inspired by a famous kitchen knife known for slicing with exceptional efficiency. The comparison reflected the shape and function of its teeth, Yet, the animal itself required no colorful title to establish its place among the greatest marine predators of the Cretaceous world. Fully grown individuals reached about 26 feet, that is nearly 8 meters, in length, and approached 5 tons in weight. That made this shark larger than any living great white shark. Its body combined powerful muscles with a streamlined outline that allowed rapid acceleration through open water. Every feature reflected an animal built for active pursuit across long distances instead of waiting patiently for prey to wander close. Its mouth carried an extraordinary supply of weapons. 7 rows of replacement teeth stood ready behind the active row, ensuring that broken teeth could be replaced throughout life. The upper jaw alone held 34 functional teeth, each growing to roughly 7 centimeters in length. Their smooth edges and curved shape formed ideal cutting tools for penetrating flesh without becoming trapped inside struggling prey. Every successful bite left behind another sharp edge prepared to take its place. Speed completed the design. Researchers estimate that Cretoxorhina mantelli could swim as fast as 70 kilometers per hour, which is about 43 miles per hour. That exceeded the estimated top speed of the modern short-fin mako shark, the fastest shark living today. Such velocity transformed brief encounters into decisive strikes. Fish, reptiles, and birds crossing the upper water column faced an attacker capable of covering surprising distances in only a few moments. Its menu demonstrates how widely that ability could be applied. Fossils preserve bite marks and embedded teeth confirming attacks on mosasaurs, long-necked plesiosaurs, giant bony fish, sea turtles, diving birds, and flying reptiles known as pterosaurs. These conclusions do not depend upon artistic interpretation. They come directly from damaged bones, broken teeth, and skeletons preserving the physical evidence of violent encounters that occurred millions of years before the first human appeared. Among the most remarkable discoveries is a single vertebra belonging to Pteranodon. Embedded firmly inside the bone rests the tooth of Cretoxorhina mantelli, preserved exactly where it entered during the attack. The tooth remained locked in place as the bone healed no further, leaving a direct record of one encounter between hunter and prey. Published in a peer-reviewed scientific study during 2018, this specimen became the first confirmed evidence that a shark had attacked a pterosaur. The fossil demonstrates that even flight offered no dependable separation from the dangers gathering below the surface. For a considerable span of the late Cretaceous, Cretoxorhina mantelli occupied the highest level of marine predation. Its combination of size, speed, endurance, and cutting power made it one of the most accomplished hunters its environment could produce. Even within an ocean already crowded with formidable life, this shark represented a standard against which other predators would eventually be measured. Its reign recorded not in legend, but in teeth, scars, and stone. Power within the Cretaceous ocean never remained fixed for long. Across millions of years, even the most successful hunter occupied only a temporary place at the top of the food web. As mosasaurs diversified into larger bodies and more specialized forms, the balance that had favored Cretoxorhina mantelli gradually began to shift. The change unfolded across generations so numerous that no single lifetime could have revealed its full direction. Yet the fossil record preserves the outcome with remarkable clarity. For roughly 18 million years, Cretoxorhina mantelli had ranked among the dominant marine predators. It hunted reptiles, fish, turtles, and flying animals approaching the sea. During that long interval, few competitors possessed the combination of speed, cutting power, and endurance required to challenge it consistently. Eventually, another lineage matured into exactly that role. Mosasaurs were no longer recent arrivals exploring coastal habitats. Many species had expanded into the open ocean, growing larger while refining bodies already shaped for pursuit and powerful attacks. The evidence for this reversal comes directly from fossil remains. Paleontologists have discovered bones of Cretaceous mantelli carrying unmistakable bite marks that match mosasaur teeth. These injuries reveal predation moving in the opposite direction from what earlier ecosystems had suggested. The shark that once attacked marine reptiles had itself become prey for some of the largest reptiles swimming beside it. Such discoveries transform an ecological hypothesis into a forensic observation recorded in stone. Timing strengthens the picture. Around 73 million years ago, Cretaceous mantelli began disappearing from the fossil record. This decline closely matches the interval when mosasaurs reached their greatest diversity and largest body sizes. Many species occupied hunting roles, ranging from agile pursuit specialists to enormous generalist predators. Their expansion reduced opportunities for older competitors, while increasing direct encounters between animals capable of challenging one another for the same food resources. Several biological advantages favored the rising reptiles. Mosasaurs produced live young directly within the ocean, allowing every generation to spend its entire life in marine environments. Different species divided available habitats instead of competing for identical prey, spreading across coastal waters, deeper seas, and even some freshwater systems. Body sizes continued increasing, providing certain individuals with enough mass and strength to overpower predators that had previously dominated those waters. Evolution rewarded flexibility, and mosasaurs displayed that flexibility across nearly every part of their anatomy and behavior. This transition illustrates a process known as ecological displacement. A successful lineage expands, diversifies, and gradually replaces another occupying a similar position within the ecosystem. No dramatic battle marks the change. Countless encounters unfold across thousands of generations until one group becomes increasingly common while the other steadily declines. The replacement emerges from accumulated advantages instead of a single, decisive event, leaving its history preserved through changing patterns of fossils across successive rock layers. The deeper lesson extends beyond either animal. The highest position in the Cretaceous ocean offered no lasting security. Every advantage invited future competition from organisms continuing to evolve under the same favorable conditions. Strength, speed, and size remained valuable, yet none guaranteed permanence. Each dominant hunter existed within an ecosystem constantly reshaping itself, where success belonged only for a time before another lineage arrived carrying adaptations better suited to the changing world. The summit of the food web remained occupied, although its occupant never stayed the same forever. Enormous reptiles and giant sharks dominated attention, yet another hunter filled the waters between them with equal determination. It belonged to the lineage of bony fish instead of reptiles or sharks, proving that formidable predators emerged from many branches of evolution during the Cretaceous. Its name was Xiphactinus audax, and although it occupied the middle layers of the food web, its size and appetite allowed it to challenge prey that would have overwhelmed most other fish. Adults commonly reached between 15 feet, that is, nearly 5 meters, and 20 feet, which is about 6 meters, in length. No larger bony fish is known from Earth's oceans, before or since. Its body resembled an enormous tarpon, stretched into a powerful swimmer with heavy jaws projecting forward. Inside those jaws stood long, fang-like teeth shaped for gripping prey securely. Unlike predators that relied upon tearing flesh into manageable pieces, Xiphactinus audax specialized in swallowing victims whole, depending upon a wide mouth and expandable throat to complete each meal. Its streamlined form also supported impressive speed. Scientists estimate that it could reach approximately 30 miles per hour, which is about 48 kilometers per hour. Such acceleration allowed sudden bursts toward schools of fish or animals moving close to the surface. Powerful lunges may even have carried its head above the water during the final moments of an attack. Every successful strike depended upon surprise, momentum, and a mouth capable of enclosing prey before escape became possible. One remarkable fossil transformed this impressive hunter into one of paleontology's most memorable discoveries. Preserved within the rock lies a Xiphactinus audax measuring about 14 feet that is nearly 4 meters, containing another fish almost half its own length. The prey, a shark named Gillicus arcuatus, remained almost perfectly preserved inside the stomach cavity. Digestion had scarcely begun. Bones rested in their natural positions, recording the final meal with astonishing clarity across millions of years. The evidence suggests an unexpected ending. The captured shark appears to have struggled violently after being swallowed. Its size proved greater than the predator could safely manage. Internal injuries or severe stress likely followed before digestion could begin. Both animals died together, leaving predator and prey enclosed within the same stone. Few fossils preserve such a complete sequence of behavior, allowing scientists to reconstruct the event with remarkable confidence from physical evidence alone. Even this powerful fish occupied an uncertain position within the wider marine community. Fossilized stomach contents from Cretaceous mantelli include remains of Xiphactinus audax, demonstrating that the giant shark regularly hunted it despite its formidable size. The relationship placed the fish in a difficult balance, capable of consuming smaller hunters while remaining vulnerable to larger ones sharing the same waters. The pattern extends even farther. Fossilized stomach contents belonging to mosasaurs also contain remains identified as Xiphactinus audax. Three successive levels of predation emerge from these discoveries. A smaller shark became food for Xiphactinus audax. That giant fish entered the stomach of Cretaceous mantelli. Some of those sharks later became meals for mosasaurs. Each connection comes from fossils preserving bones exactly where they came to rest, revealing an ocean where every successful hunter eventually encountered another one waiting farther along the chain. Among the many hunters sharing these seas, one followed a design unlike any other. Strength was not concentrated in crushing jaws or explosive speed. Its advantage emerged from shape itself, turning the outline of its body into an instrument of deception. Elasmosaurus platurus drifted through the Cretaceous Ocean with a profile that still challenges expectations, even after generations of scientific study. The animal reached lengths of nearly 50 feet, which is about 15 meters, although total size tells only part of its story. More than half of that remarkable length belonged to its neck alone, stretching almost 7 meters, which is about 4.3 miles. Wait, no correction. Stretching almost 7 kilometers would be incorrect. Stretching almost 7 meters, which is about 23 feet, the neck consisted of 72 individual cervical vertebrae, meaning 72 separate neck bones linked together in an elegant chain. Every mammal alive today follows a very different pattern. A giraffe has 7 neck bones. A blue whale has 7 neck bones. Humans also possess 7. Elasmosaurus platurus carried more than 10 times that number. Such anatomy puzzled even the earliest scientists who examined its fossils. When the first nearly complete skeleton was reconstructed during the 19th century, the extraordinary neck seemed so implausible that it was attached to the wrong end of the body. The skull was mistakenly placed where the tail belonged. Only after careful comparison with additional evidence did another paleontologist recognize the error and publicly correct the reconstruction. Reality had produced a creature stranger than familiar anatomy encouraged anyone to expect. Its head remained surprisingly small compared with the enormous body trailing behind it. Narrow jaws carried rows of slender, interlocking teeth shaped for gripping slippery prey instead of crushing shells or breaking heavy bones. Fish caught between those teeth found little opportunity to escape. The design favored accuracy over force, allowing rapid sideways movements that required little disturbance of the surrounding water. This unusual combination created a hunting method unlike that of giant sharks or mosasaurs. The heavy body could remain deeper in the water, while only the long neck extended upward. Schools of fish drifting above detected little movement because the broad torso stayed distant below them. A thin neck rising through dimmer water presented far less warning than an approaching body several meters wide. When the head entered the school, the jaws snapped shut with remarkable precision before nearby fish fully reacted. Researchers continue to debate exactly how flexible that extraordinary neck may have been. Earlier illustrations often portrayed sweeping curves resembling a serpent. More recent studies indicate that the neck probably remained much straighter, bending in gradual arcs instead of dramatic coils. Even with those limits, 72 neck bones provided exceptional reach, allowing the head to explore a large feeding space while the rest of the animal changed position very little. Within the crowded ecosystems of the late Cretaceous, this distinctive architecture occupied a different place from the giant hunters already encountered. Success came through geometry, patience, and timing woven into a body unlike any living animal. Fossils preserve every neck bone in sequence, each one adding another link to a design that once seemed impossible, until stone revealed that the ocean had shaped it exactly that way. A broad shadow crossed the warm sea with no urgency at all. Its movements carried the measured rhythm of an animal that had found its place in open water long before any observer could have imagined it. Against a backdrop of relentless hunters, Archaelonoskeros almost appeared reassuring. Its familiar outline echoed the turtles of modern beaches, offering the comforting illusion that this creature belonged to a gentler corner of natural history. The illusion faded as soon as its world came into focus. This was the largest turtle known from the history of Earth. From head to tail, it reached about 15 feet, which is about 4.6 meters. Across the span of its powerful front flippers, it measured nearly 5 meters, which is about 16 feet. Adults weighed more than 2 tons, placing them among the heaviest reptiles of their age. Every slow stroke of those enormous flippers carried the animal across broad inland seas that covered much of the continents during the late Cretaceous, allowing journeys that stretched for remarkable distances through warm marine waters. Its shell differed greatly from the heavy dome carried by living tortoises and many freshwater turtles. Instead of forming a thick suit of solid armor, the shell consisted of a lighter framework covered by tough skin. This construction reduced weight while preserving structural support, making long-distance swimming more efficient. Speed was never its defining strength, yet endurance became a valuable advantage for an animal crossing enormous marine habitats where food could appear in scattered patches separated by many kilometers, which is about many miles. Soft-bodied prey filled much of its diet. Jellyfish drifted through the water in great numbers, accompanied by squid and other animals lacking heavy protective shells. A beak built for gripping and slicing handled these meals with ease. Rather than pursuing powerful prey through rapid chases, Archelon eskyros relied on steady travel, broad vision, and an ability to exploit resources spread across immense stretches of ocean. Its lifestyle resembled endurance more than aggression, making it one of the calmer participants in an ecosystem filled with constant competition. Even so, its size offered no guarantee of security. Fossil shells preserve unmistakable bite marks that match the teeth of Cretoxurina mantelli. Other specimens carry damage matching the jaws of giant mosasaurs. These traces remain fixed in bone after tens of millions of years, providing direct evidence that the greatest shark and the greatest marine reptiles hunted the same turtle. A mature individual weighing several tons still represented a worthwhile meal whenever opportunity favored the attacker. One particularly celebrated specimen displayed today in Vienna adds another layer to its story. Growth patterns preserved within its bones indicate an age of roughly 100 years before death. Some researchers have proposed that it may have survived a prolonged period of limited food by greatly reducing its activity, conserving energy until conditions improved. That possibility cannot be proven with certainty, although the evidence suggests an animal capable of remarkable endurance across an exceptionally long life. A century of survival, an immense body, and a shell refined through millions of years of evolution still failed to place Archelon eskyros beyond the reach of predators. Within this ocean, longevity earned experience but never exemption. Every creature remained woven into the same living network, where even the oldest traveler continued its journey under the watch of larger jaws. Distance from the waves offered no promise of escape. Above the warm Cretaceous Sea, broad wings traced patient circles through rising air, following invisible currents that stretched across the flooded continents. From below, these travelers appeared almost untouchable, suspended between ocean and sky. Their lives unfolded overhead, yet every descent toward the water carried them back into the same web of hunters that governed everything beneath the surface. Among the largest of these flyers was Pteranodon. Its wings extended as much as 20 feet, which is about 6.1 meters, making it the largest flying animal known up to that point in Earth's history. Such dimensions suggest tremendous weight, although the opposite was true. An adult weighed less than a medium-sized dog. Hollow bones reduced mass while preserving strength, and an immense membrane stretched across elongated wing bones, creating an airfoil built for sustained soaring instead of continuous flapping. Once lifted by warm rising air, it could remain aloft for long periods while searching the sea below. Although often grouped with dinosaurs in popular imagination, Pteranodon belonged to an entirely separate evolutionary lineage. It was a pterosaur, sharing the landscape with dinosaurs without being one itself. That distinction reveals how many different branches of reptilian evolution occupied the same world simultaneously. Giant marine reptiles ruled the sea, dinosaurs dominated the land, and pterosaurs commanded the air, each following its own evolutionary path while remaining connected through the same living ecosystem. Feeding required Pteranodon to approach the ocean repeatedly. Its long, toothless beak skimmed close to the surface as it searched for fish moving through the upper water. Every successful meal depended upon crossing the narrow boundary between air and sea. That boundary appeared thin enough for danger to pass through in either direction. A brief touch of the water could become the final movement of an otherwise graceful flight. The fossil record preserves striking evidence of those encounters. A tooth belonging to Cretoxorhina mantelli has been discovered lodged directly within the vertebra of a pteranodon. The tooth was not found nearby or mixed with surrounding sediments. It remained embedded in the bone itself, preserving the physical moment of attack. Published during 2018, this discovery provided the first confirmed evidence that a shark had successfully attacked a pterosaur, transforming speculation into documented fact. Other discoveries broaden that picture. Fossils of the opportunistic shark, Squalocorax, preserve bones of pteranodon inside their stomach contents, indicating that smaller sharks also fed upon these flying reptiles after they landed on the sea or drifted close to its surface. Another bird occupied the same environment from a different direction. Hesperornis, a flightless diving bird adapted for underwater pursuit, hunted beneath the waves instead of above them. Fossils preserving its remains inside mosasaur stomach cavities confirm that birds entering the water also became prey for giant marine reptiles waiting below. These discoveries dissolve any clear boundary between ocean and sky. The surface marked no true separation between worlds. It formed only a narrow meeting place where wings, fins, and jaws intersected. Every descent toward the water joined the same continuous hunting ground, extending from the deepest currents upward into the open air wherever a living creature drifted close enough to be taken. A single fossil can preserve the final meal of an animal, yet a collection of fossils can reveal something much larger. Piece by piece, scattered across continents and separated by millions of years, those remains combine into a portrait of an ocean where survival depended upon constant movement through a network of hunters. Every layer of that network touched another. Every successful predator occupied a place that could vanish with a single encounter. Many modern marine ecosystems possess a broad hierarchy. Small fish are consumed by larger fish, which in turn become prey for increasingly powerful hunters. At the highest level, only a handful of species regularly threaten one another. The late Cretaceous ocean followed a different pattern. Its largest animals did not stand beyond danger. Predators frequently hunted competitors that pursued the same food, creating a web in which strength reduced risk without ever removing it entirely. The fossil record preserves these relationships with unusual clarity. Xiphactinus audax swallowed a shark measuring about 6 feet, which is about 1.8 meters, before dying with its meal still inside its stomach. Cretoxorhina mantelli fed upon Xiphactinus, leaving teeth and bite marks that document those attacks. Large mosasaurs hunted Cretoxorhina, reversing what had once been the balance between reptile and shark. The chain continues without interruption, linking hunter to hunter through evidence preserved in stone instead of speculation. Other branches of the same web reached across entirely different body designs. Mosasaurs fed upon plesiosaurs, including long-necked forms whose fossils still carry unmistakable bite marks. Some mosasaurs consumed members of their own group, showing that close relatives could become rivals as well as prey. Cannibalism and attacks upon competing species were not unusual exceptions. They formed part of an ecological system in which opportunity often outweighed familiarity. The pattern extended beyond reptiles and sharks. Pteranodon descended toward the sea to gather fish and became vulnerable to predators waiting below. Smaller sharks consumed fallen or floating pterosaurs, while larger sharks attacked living ones. Mosasaurs also captured birds that entered the water, including the diving bird Hesperornis. Even Archelon iskyros, the largest turtle known from any period in Earth's history, bears bite marks attributed to both mosasaurs and Cretaceous. Great size, protective anatomy, and long life offered advantages, although none provided complete security. Paleontologists describe this pattern with the term intraguild predation. It refers to animals that compete for similar prey while also hunting one another. Instead of occupying separate levels, rival predators overlap, sharing food resources and sometimes becoming food themselves. Evidence from the late Cretaceous indicates that this form of interaction occurred across more groups and more body sizes than in any other marine ecosystem presently recognized in the fossil record. Viewed together, these discoveries reveal remarkable order instead of confusion. Every species filled a recognizable ecological role, yet no role granted lasting protection. Surface waters, deeper channels, coastal shallows, and open seas all belong to overlapping hunters whose lives intersected repeatedly. The structure remained stable because every connection balanced another, even as individual fortunes shifted. Within that immense living network, survival depended less upon occupying the highest position than upon enduring another day inside a system that granted no permanent exemptions. The story of this ocean survives through moments that never had an opportunity to fade. Each fossil preserves an instant interrupted, a life halted before movement could continue. Collected across distant coastlines and separated by immense spans of time, these discoveries do more than reveal which creatures existed. They preserve encounters, injuries, meals, and struggles with remarkable precision. From these fragments, paleontologists reconstruct relationships that no observer could ever have witnessed directly. Marine rocks from the heart of North America hold some of the richest records, where layers of chalk and shale accumulated beneath broad inland seas. Across the Atlantic, the Kem beds of Morocco preserve another chapter of the same marine world. Coastal deposits in Angola contribute additional evidence, while marine fossil sites in New Zealand extend the picture across the opposite side of the globe. Together, these formations document an ecosystem spread across ancient oceans instead of a single isolated region. Their greatest strength lies in the kind of evidence they preserve. Entire skeletons are valuable, although skeletons alone reveal only anatomy. Far more revealing are stomach contents, teeth lodged inside bone, scars that healed during life, and bones still lying together exactly where predator and prey came to rest. These remains function almost like evidence collected from a modern investigation, allowing scientists to identify individual acts of predation rather than merely listing the animals that shared the same waters. One celebrated example comes from Xiphictinus audax, preserved with another fish still occupying its stomach cavity. The swallowed animal remained almost completely intact because digestion had scarcely begun before the larger predator died. That extraordinary specimen demonstrates that even powerful middle-level hunters accepted dangerous prey, sometimes with fatal consequences. It transforms an ordinary fossil into a frozen sequence of behavior, preserving both participants in a single piece of stone. Other discoveries reveal predators from higher positions in the food web. Fossils of Cretaceous mantelli preserve hardened stomach contents containing fragments of mosasaur bone. Those remains confirm direct attacks upon large marine reptiles instead of indirect association. A vertebra belonging to Pteranodon still contains a tooth from Cretaceous, providing unmistakable evidence that a flying reptile entered the reach of a shark. Mosasaur skeletons preserving unborn young within the abdominal cavity establish that these reptiles gave birth to living offspring in open water. Elasmosaurus fossils, marked by mosasaur bites, show that the longest neck in the sea provided no lasting protection. During the 19th century, fossil collector Charles Sternberg described excavating these marine deposits as uncovering a battlefield. His observation referred less to broken bones than to the astonishing concentration of interactions preserved within them. Nearly every excavation exposed another sign that one creature had encountered another in direct conflict. Tooth met bone, prey entered stomach, wounds healed or failed to heal, and every layer added another page to the same enduring account. Taken together, these discoveries create something more substantial than imaginative reconstruction. They establish a chain of physical evidence extending across continents and generations of research. The late Cretaceous ocean emerges through traces left by real animals engaged in ordinary acts of feeding, defending, pursuing, and surviving. Stone became the archive, and time preserved each fragment with enough fidelity that the vanished sea can still speak through its scars. Few extinct predators leave behind a menu detailed enough to read almost item by item. Mosasaurs are among those rare exceptions. Their stomach contents, combined with bite marks preserved on bones scattered across multiple fossil sites, provide one of the clearest dietary records known for any extinct vertebrate. Together, they reveal hunters that accepted almost every opportunity the sea presented, moving through their world with remarkable flexibility instead of relying upon a narrow selection of prey. The recovered evidence includes bony fish of many sizes, sharks ranging from smaller species to the formidable Cretoxorhina mantelli, sea turtles including Archelonischyros, long-necked plesiosaurs including Elasmosaurus, Platurus, spiral-shelled ammonites, squid-like belemnites, seabirds, the flightless diving bird Hesperornis, pterosaurs, and even other mosasaurs. Each discovery adds another confirmed interaction instead of another assumption. The remarkable breadth of this list shows predators capable of exploiting nearly every corner of the marine ecosystem. Among these prey animals, ammonites occupied a role somewhat similar to that of the modern nautilus. Their coiled shells drifted through Cretaceous seas in extraordinary abundance, providing food for many marine hunters. Mosasaurs consume them alongside swift fish, reptiles, and other available prey. Such variety required more than strength alone. It demanded anatomical versatility, capable of handling prey with dramatically different shapes, defenses, and behaviors without forcing the hunter to specialize too narrowly. The skull of Mosasaurus hoffmanii reflects exactly that versatility. Toward the front of the jaws, long pointed teeth pierced and secured struggling animals before escape became possible. Farther back, broader and more durable teeth applied crushing force against tougher prey, including shelled cephalopods. This arrangement allowed the same predator to capture a slippery fish during one hunt and process a heavily protected ammonite during the next, adapting without requiring a different feeding strategy for each encounter. Additional equipment waited beyond the visible jaws. Along the roof of the mouth sat a second working row of teeth, known as pterygoid teeth. Once prey passed between the outer jaws, these inward-pointing teeth prevented retreat, drawing each movement deeper into the throat. The lower jaws also possessed a modest degree of flexibility, allowing the mouth to widen beyond its resting position. Large prey, therefore, became manageable, even when its body exceeded what the closed jaws appeared capable of accepting. Evidence from tooth wear, microscopic damage, and chemical signatures preserved within fossilized teeth reveals another important pattern. Different mosasaur species consistently consumed different proportions of available prey. Some favored harder-shelled animals, while others concentrated more heavily on fish or large reptiles. This ecological partitioning reduced direct competition by dividing resources across numerous closely related species. Many formidable hunters, therefore, occupied the same sea without exhausting identical food supplies or driving one another toward constant conflict. Viewed together, these discoveries define opportunism with unusual clarity. Mosasaurs possessed the tools to seize almost anything they could overpower, while different species refined those abilities toward slightly different preferences. Their diet stretched across nearly every major branch of marine life, from shelled invertebrates to fellow apex predators. If an animal entered reach, and the balance of size and circumstance favored the hunter, some mosasaur species almost certainly counted it among its next meal. Maps of the modern world encourage the comforting impression that oceans occupy familiar boundaries. During the late Cretaceous, those boundaries dissolved. Water advanced across continents with remarkable persistence, reshaping coastlines until shore became an uncertain idea. The scale of this transformation was measured not only by the creatures filling those waters, but by the amount of Earth they claimed as their domain. Global sea levels stood roughly 100 to 200 meters higher than they do today. That increase, which is about 328 to 656 feet, or about 100 to 200 meters, did far more than flood beaches. It submerged immense stretches of low-lying land, replacing forests, river valleys, and plains with broad inland seas, places that modern communities cultivate, build upon, and cross by road once lay beneath warm marine water extending far beyond any present coastline. One of the greatest examples stretched through the heart of North America. An inland sea reached from what is now Texas northward toward the Arctic, dividing the continent into separate landmasses for millions of years. Similar flooding covered large parts of interior Europe, spread across significant portions of North Africa, entered sections of South America's interior, and reached landscapes that today stand hundreds of kilometers, which is about 62 miles, from the nearest shore. The familiar arrangement of continents had become something altogether different. These flooded basins were extensive, although they remained comparatively shallow. Many reached depths of only 800 to 900 meters, that is nearly 2,625 to 2,953 feet. Such dimensions created productive marine habitats from the seafloor upward. Sunlight penetrated much of the water column, supporting microscopic plankton, abundant fish, marine reptiles, and countless invertebrates. Food circulated through nearly every level, allowing predators to patrol from the bottom to the surface without entering an immense, lightless abyss. That shallowness also changed the meaning of distance. The seabed never disappeared into an unreachable gulf far below. Animals moving near the surface occupied the same connected environment as creatures feeding close to the bottom. Energy flowed efficiently through this relatively compressed ecosystem, sustaining remarkable biological richness. Predators capable of traveling through different depths encountered opportunities almost everywhere they searched, while prey found comparatively few regions where isolation offered lasting security. As seawater continued spreading inland, dry ground became progressively more limited. Coastlines retreated across plains, estuaries expanded, and familiar terrestrial habitats contracted. Land animals adapted by shifting their ranges or becoming confined to remaining uplands, while marine ecosystems followed the advancing shoreline. Every new embayment and inland channel carried fish, reptiles, sharks, mollusks, and countless smaller organisms farther across the continents, extending ecological relationships into places that had once belonged entirely to life on land. The Cretaceous Ocean, therefore, existed as more than a distant expanse beyond the horizon. It wrapped itself around continents, crossed them, and transformed their interiors into living seas. Wherever its waters settled, complete ecosystems arrived together, carrying hunters, grazers, scavengers, drifting plankton, and every intricate connection between them. The remarkable creatures already encountered did not inhabit isolated pockets scattered across the globe. They occupied an immense marine world whose reach extended across much of the planet itself, making the ocean one of the defining landscapes of its age. Life in the Cretaceous Ocean did not begin with shelter. For mosasaurs, the first moment of existence unfolded in open water, surrounded by the same predators that shaped every later chapter of their lives. A remarkable fossil discovered in what is now South Dakota preserves 5 unborn young inside the abdominal cavity of an adult female. Their arrangement leaves little doubt that mosasaurs gave birth directly into the sea, never returning to land to lay eggs or guard nests along a shoreline. That reproductive strategy carried clear advantages. Mothers remained within the marine environment throughout their lives, avoiding dangerous journeys onto land and allowing the lineage to occupy oceans continuously. At the same time, each newborn entered an ecosystem already filled with hunters. A juvenile small enough to fit comfortably inside the jaws of a giant bony fish faced danger almost immediately. Around it swam swift predators such as Ixopectinus audax, formidable sharks including Cretoxorina mantelli, and adult mosasaurs many times its own size. The fossil record shows that those adult mosasaurs could themselves become a threat. Bite marks preserved on juvenile remains, together with stomach contents containing bones from younger members of the same genus, demonstrate that cannibalism formed part of their ecology. Competition for food did not pause because two animals shared close ancestry. When circumstances favored the larger individual, even its own relatives could become prey. The distinction between family and food disappeared within the broader pressures of survival. Scientists describe one likely response to such relentless mortality through a reproductive pattern known as R selection. In this strategy, animals produce many offspring because only a fraction are expected to survive into adulthood. High losses among juveniles become part of the normal balance of the population rather than an unusual event. This approach appears repeatedly in environments where young animals experience intense predation from the moment they begin independent life, making numbers as important as parental investment. For mosasaurs, that pattern helps explain how an enormously successful dynasty persisted for millions of years despite extraordinary hazards. Every generation produced enough newborns that some escaped the countless threats surrounding them. Those survivors matured, reproduced, and contributed another wave of offspring to the same demanding ecosystem. Population stability, therefore, emerged through continual replacement instead of widespread survival among individual juveniles. The lineage endured because probability favored persistence across many births, even when individual lives often remained brief. Growth brought greater strength, although it never brought complete security. Juveniles became prey for larger reptiles, sharks, and giant fish. Subadults could fall victim to even larger mosasaurs occupying the same waters. Full-grown adults sometimes attacked one another, and the fossil evidence shows that the largest species occasionally consumed smaller relatives. Every increase in size shifted the balance of risk without eliminating it entirely. Advancement through life reduced certain dangers while introducing others shaped by competition within the same formidable lineage. Seen across an entire lifetime, survival became less like a permanent condition and more like a series of successful passages through successive challenges. Birth offered no sanctuary. Youth carried continual exposure. Maturity demanded constant awareness of rivals that shared the same hunting grounds. Even dominance required renewal with every encounter. The Cretaceous ocean sustained magnificent predators, yet none received exemption from the rules governing the world that had given them life. The shoreline, once imagined as a boundary between worlds, became far less certain as the story of mosasaurs continued to unfold. Fossils preserved in rocks, far from the great inland seas, revealed a pattern that bones alone could not explain. The answer emerged from chemistry locked inside their teeth, preserving traces of waters crossed millions of years before the animals themselves vanished. Scientists reached this conclusion through isotopic analysis, a chemical technique that examines elemental signatures preserved inside fossil material. As a tooth grows, it incorporates oxygen from the water an animal drinks or swims through. Salt water and fresh water contain different oxygen isotope ratios, and those differences become permanently recorded within the forming enamel. Long after flesh has disappeared, those chemical signatures remain, allowing researchers to reconstruct the environments an animal physically inhabited while each tooth was developing. When this technique was applied to certain mosasaur fossils, the results expanded their known world. Some individuals carried chemical patterns matching fresh water or brackish water instead of fully marine conditions. These signatures represented extended residence rather than brief visits. The teeth were not recording a short excursion through a river mouth. They reflected prolonged periods spent away from the open ocean, in waterways where the chemistry remained distinctly different from the surrounding seas. An even more striking discovery came from what is now Hungary. There, paleontologists uncovered the remains of a freshwater mosasauroid preserved within deposits lacking any known connection to a Cretaceous marine environment. The surrounding rocks indicated an inland freshwater ecosystem rather than a coastal setting. This animal had not wandered accidentally into an isolated river. Its entire existence unfolded within waters separated from the great oceans, revealing that one branch of this remarkable lineage had established itself far beyond its ancestral home. Other evidence points toward a broader pattern. Smaller mosasaur species repeatedly display freshwater chemical signatures, suggesting that some lineages were adapting to rivers and inland waterways as permanent habitats. Their bodies still reflected their marine ancestry, yet their lives increasingly unfolded among channels, floodplains, and lakes connected through freshwater systems. Evolution was gradually extending the reach of these reptiles into environments once occupied by very different predators. As the late Cretaceous progressed, that expansion carried important consequences for the rest of the landscape. Rising seas had already reduced the amount of dry land available across many regions. Rivers crossing those remaining land masses became natural corridors rich with fish and other prey. Following those food sources upstream required no dramatic transformation, only gradual adaptation over many generations. The movement of mosasaurs into these waterways represented another step in the continual widening of their ecological range. This changing geography blurred distinctions that once seemed dependable. Open ocean, inland sea, estuary, and river became connected parts of one living network. Predators capable of traveling between those environments dissolved boundaries that earlier ecosystems might have maintained. A creature entering fresh water could no longer assume it had left marine hunters behind because some of those hunters had already followed the same route inland. Viewed together, the fossils and their chemical record describe a world where apex predation extended wherever suitable water remained. The broad ocean supported it first, shallow inland seas sustained it next. River systems gradually became part of the same expanding domain. Across the Cretaceous landscape, no enduring body of water can be shown to have stood entirely beyond the reach of those formidable reptiles, whose journey carried them wherever flowing water offered another place to live and hunt. Life had learned to navigate jaws, teeth, speed, and ambush. Yet another threat drifted through the Cretaceous seas without chasing anything at all. It arrived through the water itself, carried by chemistry that no animal could outrun. Even the greatest hunters depended upon dissolved oxygen, and there were intervals when the ocean gradually surrendered that essential resource across immense regions. The underlying process begins with a simple physical principle. Warm water holds less dissolved oxygen than cold water. Throughout the Cretaceous, global temperatures remained high enough for that effect to influence enormous marine basins. When circulation weakened and fresh oxygen failed to mix into deeper layers, those waters lost more and more of the oxygen required by most animals. Fish, reptiles, mollusks, and countless other organisms all depended upon that invisible supply, regardless of their size or place within the food web. Scientists describe these episodes as oceanic anoxic events. The word anoxic means oxygen depleted, referring to water where dissolved oxygen has fallen to levels incapable of supporting most oxygen breathing marine life. These were not local accidents confined to isolated bays. They spread across huge portions of the world's oceans, transforming productive habitats into environments where survival became increasingly difficult and, in many places, impossible. The most severe event presently recognized occurred about 93.5 million years ago. Known to researchers as Oceanic Anoxic Event 2, it endured for as long as 700,000 years, approximately twice the entire history of modern humans as a species. During that extraordinary interval, scientific estimates suggest that as much as one half of Earth's total ocean volume became anoxic. A dead zone on such a scale reshaped the living planet over spans of time almost impossible to imagine from a human perspective. Evidence for these events rests within dark rock layers preserved on multiple continents. Geologists identify extensive bands of black shale formed when enormous amounts of organic material settled onto the seafloor without decomposing. Under ordinary conditions, oxygen supports organisms that break down dead matter. During prolonged oxygen depletion, that process faltered, allowing thick accumulations of carbon-rich sediment to build layer upon layer. Those rocks remain as enduring records of oceans transformed by chemistry instead of claws. Marine ecosystems responded with sweeping change. Entire populations disappeared from affected regions as oxygen vanished from their habitat. Food chains unraveled because prey declined alongside predators. Ecological spaces emptied, leaving opportunities for survivors capable of enduring altered conditions or expanding rapidly after oxygen returned. Evolution continued through these intervals, with adaptable lineages spreading into places where earlier communities had collapsed. The balance of the ocean shifted repeatedly, shaped by environmental upheaval as much as biological competition. Predation never disappeared during these episodes, though it unfolded within a changing stage. Animals already adapted for resilience gained advantages when familiar ecosystems fractured. Those able to exploit new opportunities persisted, while less flexible lineages faded from the record. The ocean remained full of hunters, yet the greatest force directing their fortunes could arrive without teeth, fins, or powerful muscles. Seen together with the living creatures already encountered, these chemical crises reveal another dimension of the Cretaceous Sea. Danger emerged from predators crossing the water, and it also emerged from the water itself. The same ocean that nourished extraordinary abundance could, across immense distances and astonishing spans of time, withdraw the very breath upon which that abundance depended. Ledison. Across broad chalk hills and weathered shale slopes, the past has never remained entirely buried. Each season, rain loosens fragments from ancient layers. Streams carry teeth into gravel beds, wind exposes vertebrae along dry ridges, and white cliffs gradually release bones that have rested unchanged since the closing chapters of the Cretaceous. Long before paleontology assembled names and classifications, these remains already lay within reach of anyone willing to notice what the ground revealed. For thousands of years, Native American peoples living across the Great Plains encountered these fossils as part of the landscape itself. Generations passed while families hunted, traveled, gathered food, and crossed country where marine reptiles and flying reptiles emerged naturally from the rock. The discoveries did not arrive through museums or scientific expeditions. They appeared during ordinary life, carried into daylight by erosion that never truly stopped. Oral traditions, recorded independently by anthropologists from multiple nations, preserve strikingly similar themes. They tell of immense water beings and enormous creatures of the air locked in violent encounters. Some stories describe great serpentine forms rising from lakes or rivers to seize animals overhead. Others speak of winged beings drawn downward into waiting waters. Details vary from one tradition to another, as living stories naturally do across cultures and generations. Yet the recurring relationship between sky and water appears with remarkable persistence. In 2005, paleontologist Adrian Mayer brought renewed attention to an intriguing geographical pattern, examining documented traditions alongside fossil localities. She observed that many stories featuring conflicts between giant water creatures and aerial beings were concentrated in regions where mosasaur and pterosaur fossils occur together within the same Cretaceous rock formations. The correspondence did not attempt to transform oral tradition into scientific data. Instead, it highlighted that communities repeatedly developed comparable explanations while living among the same extraordinary physical evidence. The fossils themselves offer a straightforward connection. Giant marine reptiles and giant flying reptiles occupied the same ecosystems during the closing age of dinosaurs. Their remains settled into sediments that later hardened into chalk and shale. Millions of years afterward, erosion exposed bones from both animals in the same landscapes. A person discovering those remains without modern biology would naturally seek an explanation drawn from direct observation. Enormous jaws and immense wings emerging from neighboring rocks suggest lives that once intersected. From a modern perspective, paleontology eventually supplied the missing identities. The sea creature became a mosasaur, the soaring reptile became a pterosaur. Fossil evidence later demonstrated that these animals truly shared the same waters, and physical traces preserved in bone-confirmed interactions between predators below and flyers above. Scientific reconstruction expanded the picture, though it began with the same stone evidence visible to earlier observers. Those enduring traditions therefore occupy an unusual place beside the fossil record. They preserve human attempts to understand discoveries encountered without the vocabulary of geology or evolutionary biology. Their creators did not invent those immense bones. They interpreted them using the knowledge available within their own worlds, weaving observation into stories capable of carrying memory across centuries. The rocks remained unchanged through every retelling. They continued offering the same scattered teeth, weathered vertebrae, and fragments of wing. Long before laboratories measured them and museums displayed them, the landscape had already introduced those forgotten creatures to human imagination, allowing the fossils themselves to begin telling their history. The closing millions of years of the Cretaceous marked the fullest expression of a lineage that had begun with modest reptiles moving along shorelines. Between roughly 72 and 66 million years ago, mosasaurs reached their greatest extent in every measurable way. Their bodies became larger, their species more numerous, and their distribution expanded until they occupied marine habitats across the planet with astonishing consistency. Among the largest stood Mosasaurus and Hanosaurus, each exceeding 15 meters in length, which is about 49 feet. Their proportions rivaled the largest terrestrial hunters of their age, though their influence stretched far beyond any single continent. Wherever broad seas connected coastlines, these marine reptiles had already established themselves. Fossils recovered from Europe, Africa, North America, South America, Antarctica, and regions once bordering the ancient Pacific Ocean reveal an animal family that had become almost universal across Earth's waters. Their achievement was exceptional for another reason. Less than 30 million years earlier, their ancestors had still belonged to a group of land-dwelling lizards. Evolution transformed those reptiles into streamlined swimmers with powerful tails, paddle-shaped limbs, and skulls equipped for seizing an extraordinary range of prey. Within a comparatively brief geological interval, one evolutionary family assumed the highest predatory position throughout every major ocean basin known from the fossil record. This dominance extended across environments instead of remaining limited to a single setting. Large species cruised open seas, while others hunted coastal shallows rich with fish and shelled animals. Evidence from fossil chemistry indicates that smaller members of the broader mosasaur group entered river systems, carrying their lineage beyond salt water into fresh and mixed water habitats. From the sunlit surface to deeper marine passages, their relatives occupied ecological roles with remarkable flexibility. Few predator groups before or afterward displayed such breadth at the same moment in Earth's history. Modern comparisons inevitably fall short. Killer whales share broad diets and global distributions, yet they remain mammals dependent upon coordinated social hunting, and they occupy a narrower collection of ecological roles. Late Cretaceous mosasaurs diversified into many forms simultaneously, each specializing in different prey while remaining members of the same evolutionary family. Their combined presence created an influence extending across nearly every productive marine habitat known from that age. Even this remarkable success carried no promise of security. Fossil stomach contents, damaged skeletons, and healed bite marks reveal repeated encounters between mosasaurs themselves. Larger individuals consumed smaller relatives. Juveniles faced danger from adults belonging to their own genus, while mature animals risked confrontation with rivals of equal or greater size. Dominance did not erase vulnerability. It merely shifted the source of danger toward members of the same lineage. The resulting ecosystem reached a condition without known precedent. Every important marine niche held an accomplished predator, each linked to the others through competition, opportunity, and continual adaptation. The highest position in the food web belonged to animals that had once walked upon land, and they maintained that place across the world through persistence rather than permanence. Their reign represented the fullest development of predation before the final days of the Cretaceous brought an entirely different chapter to Earth's history. There came a moment when the greatest hunters on Earth remained exactly as powerful as they had been the day before, yet their fate had already been decided. The change began far from their jaws and muscles, beyond the reach of speed or strength. It arrived from the sky, carrying consequences that spread through every ocean with relentless patience. 66 million years ago, an asteroid approximately 10 to 15 kilometers across, which is about 6.2 to 9.3 miles, struck what is now the Yucatan Peninsula of Mexico. It approached at roughly 20 kilometers per second, which is about 12.4 miles per second, releasing energy beyond any event witnessed during human history. Molten debris blasted into the atmosphere before falling back across the planet. As those fragments returned, they heated the air enough to ignite widespread wildfires. Dust, soot, and vapor then rose high above the surface, forming a veil that wrapped around the globe. Within weeks, sunlight reaching Earth's surface declined sharply. Temperatures fell as the atmosphere emitted far less energy from the sunday. Forests, coastlines, and inland waters entered unfamiliar conditions. Across the oceans, the greatest disruption remained almost impossible to see because it unfolded among organisms measured in fractions of a millimeter. Phytoplankton, microscopic living cells drifting through sunlit seawater, form the foundation of marine ecosystems because they create food through photosynthesis. Without sufficient sunlight, that process faltered. As months stretched onward, immense populations declined across large regions of the ocean. The interruption reached far beyond those tiny organisms. Their disappearance removed the primary food source, sustaining the countless animals immediately above them. Zooplankton depended upon phytoplankton for nourishment. Small fishes depended upon zooplankton. Larger fishes depended upon those smaller fishes. Marine reptiles, sharks, seabirds, and every predator occupying higher positions relied upon the continuous flow of energy, beginning with microscopic life near the surface. Each level supported the next through ordinary feeding relationships that had endured across millions of years. Once the foundation weakened, every connection above it began to fail in sequence. Mosasaurs did not vanish because another hunter surpassed them. Their powerful jaws remained capable of crushing shells and gripping struggling prey. Their streamlined bodies still crossed the water with remarkable efficiency. Their senses continued searching for movement through seas that no longer produced enough living food to sustain the immense network supporting them. Hunger spread upward through the food web until it reached even the largest individuals. An apex predator measuring about 57 feet, which is about 17 meters, represented nearly 25 million years of evolutionary success. That immense history ended through the disappearance of organisms invisible to the unaided eye. The smallest inhabitants of the ocean proved inseparable from its greatest rulers, linked through relationships established long before the final catastrophe arrived. The world that followed contained seas once again filled with life, though their rulers belonged to different lineages and different ages. The immense system of predation that had perfected itself over millions of years did not collapse beneath a stronger rival. It dissolved because the first link in its chain disappeared, carrying every link above it toward the same ending, until the great hunters themselves drifted into the fossil record they would leave behind. A thin layer of rock separates two worlds. Across countless cliffs and exposed landscapes, that boundary appears as little more than a narrow band, yet everything above it tells a different story from everything below. The difference is so complete that the missing animals become as meaningful as the fossils that remain. In sediments deposited immediately after the Cretaceous Paleogene extinction boundary, the familiar rulers of the late Cretaceous ocean disappear together. No mosasaurs return. No plesiosaurs continue their long history. No giant marine reptiles of any kind appear in the layers that follow. The swift fish known as Xiphactinus is gone. The great shark Cretoxorhina is gone as well. Their absence repeats across continents, preserved wherever rocks of the appropriate age remain exposed. Paleontology often speaks through discoveries, yet here it speaks through disappearance. The creatures that endured belonged to a different pattern of life. Some shark lineages survived. Certain groups of bony fish remained. Various marine invertebrates continued through the crisis. These survivors generally shared qualities that favored persistence during prolonged ecological collapse. Smaller bodies required fewer resources. Flexible feeding habits allowed them to exploit whatever food remained available. Broad tolerance for changing conditions became more valuable than specialization. They inherited an ocean stripped of much of its former complexity, carrying forward life without restoring the vanished order that had existed before. Recovery unfolded with extraordinary patience. Marine ecosystems could not immediately support giant hunters because the lower levels of the food web first needed to rebuild. Microscopic producers expanded. Countless small animals followed. Larger prey gradually returned as ecological connections strengthened across millions of years. Each layer depended upon the stability of the one beneath it. Until those foundations matured once again, enormous predators found no place within the recovering seas. For roughly 10 to 15 million years, which is about 6.2 to 9.3 miles, no, correction, that span describes time rather than distance, the oceans lacked marine predators approaching the scale that had dominated the closing chapters of the Cretaceous. Geological history records many recoveries, although this one advanced with measured persistence. Entire communities formed anew before bodies of exceptional size could once again be sustained by the available energy flowing through marine ecosystems. Eventually, another lineage began an entirely different journey. Around 50 million years ago, approximately 16 million years after the extinction, certain land mammals entered coastal waters and gradually adapted to life at sea. These early whales descended from terrestrial ancestors rather than marine reptiles. Their transformation required millions more years before some species reached dimensions comparable with the largest mosasaurs. The path toward giant size had to be built again from its earliest stages, following different anatomical solutions within a different biological heritage. The seas that emerged from this immense interval belong to another age. Familiar coastlines returned, currents continued their endless circulation, and sunlight still reached the surface each morning. Even so, the structure supporting life had been rewritten. The predators, the prey, and the relationships connecting them no longer matched the world buried beneath the boundary layer. Earth did not restore the vanished ocean. It composed another one, shaped by new survivors and guided by new possibilities. The seas surrounding the modern world carry familiar rhythms of waves and tides, yet their living architecture belongs to a story that began after an older one had already ended. Every large predator moving through today's oceans descends from survivors that rebuilt marine ecosystems piece by piece. None inherited the ecological order that had once supported the great marine reptiles. They occupy a world assembled from fresh beginnings, following evolutionary paths that diverged long after the disappearance of the Cretaceous giants. Among living sharks, the great white represents one of the most formidable hunters. Descended from shark lineages that endured the mass extinction, it eventually reached lengths of about 20 feet, which is about 6 meters. Even at its largest, it measures roughly one-third the length of Mosasaurus hoffmanii. Its hunting style also reflects a different ecological setting. Great white sharks rely heavily upon concealment, bursts of acceleration, and carefully timed attacks. They dominate particular habitats, although they do not roam every marine environment with the broad ecological reach once achieved by the largest mosasaurs. Another lineage reached extraordinary size through an entirely separate history. Sperm whales, the largest toothed predators alive today, may grow to approximately 60 feet, which is about 18 meters. Their ancestors were hoofed land mammals that gradually entered coastal waters around 50 million years ago. Countless generations reshaped limbs into flippers, altered hearing for underwater life, and transformed breathing, swimming, and feeding until these whales became masters of the deep. Their immense bodies emerged through more than 50 million years of evolution, more than twice the span during which mosasaurs rose from small terrestrial lizards to global apex predators. Orcas illustrate another solution to marine predation. Their strength comes as much from social knowledge as physical ability. Family groups remain together for decades, passing hunting traditions from one generation to the next. Different populations specialize in different prey, including fish, seals, rays, and even large whales. Cooperation allows them to overcome animals far larger than any single individual could subdue alone. Intelligence, communication, and shared experience shape their success, creating a strategy fundamentally unlike the solitary dominance practiced by the great marine reptiles of the late Cretaceous. Equally revealing is what no longer exists. Great white sharks do not routinely hunt adult sperm whales. Sperm whales do not normally prey upon adult orcas. Orcas may occasionally attack young sharks or vulnerable whales, yet sustained warfare among the largest marine predators is not the defining pattern of today's oceans. The highest levels of the food web remain more clearly separated, reducing the continual overlap that once placed giant hunters in direct conflict with one another. Modern seas, therefore, cannot be understood as softened versions of the Cretaceous world. Their structure differs from its foundation upward. Predator communities occupy distinct roles. Food webs contain broader separation between ecological levels, and evolutionary history followed entirely different routes after the earlier system vanished. The waters covering Earth today preserve immense beauty and formidable hunters, although they belong to an ocean rebuilt from survival, not one continuing uninterrupted from the age when marine reptiles ruled every horizon. Each field season begins with the possibility that a layer of stone, untouched for millions of years, still holds a page no one has read. The history of the Cretaceous ocean remains unfinished, not because the evidence is scarce, but because so much of it continues to emerge from cliffs, deserts, river valleys, and coastal outcrops across the world. Every carefully prepared fossil has the potential to widen the picture rather than complete it. For many years, knowledge of mosasaurs depended heavily upon discoveries from North America. That foundation has steadily expanded as new specimens have appeared across other continents. Morocco's Kem beds continue to yield remarkable material representing previously unknown species, and ecological diversity. Angola has revealed marine reptiles from coastlines that once bordered the southern Atlantic Ocean during its early development. New Zealand has produced fossils showing that these predators reached seas far from the regions once considered their principal strongholds. Together, these discoveries demonstrate a dynasty whose distribution and variety exceeded earlier expectations, stretching across nearly every major marine environment of the late Cretaceous. Fresh discoveries have altered ideas about behavior as well as geography. Research published during the year 2024 used biomechanical modeling to examine the movement of Mosasaurus hoffmanii. Earlier interpretations often emphasized surprise attacks launched over short distances. The new analysis suggests a broader range of capability, indicating that large mosasaurs may also have sustained high-speed pursuit over meaningful distances before overtaking prey. This raises the estimated performance of the largest species beyond previous assumptions, presenting an animal capable of combining endurance with explosive power according to the circumstances it encountered. Some of the most valuable fossils preserve far more than bone. One remarkable specimen of plate carpus retained impressions of scales together with traces of internal organs. Such preservation is extraordinarily uncommon among large vertebrates. These remains provide the first direct evidence of soft tissues in a mosasaur, allowing researchers to investigate aspects of anatomy that skeletons alone cannot reveal. Details of body shape, skin covering, and organ arrangement become accessible through evidence that survived by exceptional chance, opening avenues of research unavailable only a generation ago. Chemical investigation continues to transform understanding in similar ways. Scientists are expanding isotopic mapping of mosasaur fossils recovered from freshwater and brackish deposits. This technique examines elemental signatures preserved within fossilized teeth and bones, revealing the environments inhabited while those tissues formed. Each newly sampled specimen refines the map of rivers and inland waterways explored by different species. Additional fossil localities continue to be identified, leaving the full extent of freshwater colonization unresolved and inviting further discovery. Viewed together, these advances point in a consistent direction. The Cretaceous Ocean appears increasingly intricate with every passing decade. Predator behavior proves more versatile, geographic distribution grows broader, ecological relationships become richer, and physiology emerges in greater detail than earlier generations imagined possible. The familiar outline remains recognizable, although its edges continue to expand. Science therefore moves forward through accumulation rather than certainty. Every newly uncovered skeleton, every preserved tooth, every layer of sediment, and every chemical signature adds another sentence to a narrative still being assembled. The ceiling of understanding continues to rise, and each addition suggests that the living ocean of the late Cretaceous possessed even greater complexity than the remarkable picture already revealed by the rocks. There is a tendency to imagine the Cretaceous world as something separated from the present by an unbridgeable gulf governed by conditions that could never exist again. The rocks suggest a different perspective. The forces that shaped those oceans were not extraordinary exceptions to the laws of nature. They emerged from physical variables that can be measured, tested, and compared across time, leaving behind evidence that remains accessible in sediments, fossils, and chemistry. One of those variables is the concentration of carbon dioxide in the atmosphere. Geological evidence indicates that during much of the Cretaceous, atmospheric carbon dioxide approached approximately 2,000 parts per million. Modern measurements record levels above 420 parts per million, still well below the values reconstructed for the Cretaceous world, yet increasing compared with earlier centuries. The comparison does not imply identical outcomes, since continents, ocean circulation, and many other conditions differ today. It demonstrates that atmospheric composition is a measurable quantity capable of changing across Earth's history. Ocean temperature provides another point of comparison. Some Cretaceous surface waters reached about 35 degrees Celsius or 95 degrees Fahrenheit, especially in tropical regions where prolonged warmth extended across immense areas. Modern observations show that average ocean surface temperatures have continued to rise, with many of the warmest years recorded during the past decade. Although present conditions remain far below those Cretaceous extremes on a global scale, the governing relationship between atmospheric warming and ocean temperature remains grounded in the same physical principles. Sea level tells a similar story through a different measure. During the Cretaceous, global seas stood roughly 100 to 200 meters above those of the present day, which is about 328 to 656 feet, or approximately 100 to 200 meters. Modern projections under different warming scenarios involve changes measured in meters rather than hundreds of meters. Even so, both records illustrate that sea level responds to changing climate over time, altering coastlines and reshaping marine habitats as conditions evolve. The chemistry of oxygen within seawater follows another enduring rule. Warm water naturally holds less dissolved oxygen than colder water. That relationship contributed to the oxygen depleted intervals explored earlier, when extensive portions of the Cretaceous ocean lost enough oxygen to transform entire ecosystems. Today, researchers have documented expanding oxygen minimum zones in several parts of the modern ocean. The scale differs greatly from the largest Cretaceous events, yet the underlying chemistry remains the same because the properties of water have not changed. These observations are descriptive rather than predictive. They do not determine what future oceans must become, nor do they support a single, inevitable path. They establish that the variables responsible for shaping Earth's marine environments can be observed directly, measured with precision, and followed through both geological history and modern scientific records. The Cretaceous ocean, therefore, belongs neither to legend nor to imagination. It represents one documented outcome produced by identifiable physical conditions acting over immense spans of time. Those conditions are understandable today through evidence preserved in stone, water, and atmosphere, reminding us that Earth's history was written by natural processes that continue to operate according to the same enduring laws. Looking across the span of this vanished ocean, one realization settles with unusual clarity. The story has never belonged to a single predator alone. It belongs to evolution itself, revealing what becomes possible when opportunity appears, competition shifts, and the living world discovers an empty role waiting to be filled. The mosasaur lineage stands among the clearest demonstrations in the vertebrate fossil record of how rapidly profound transformation can unfold under the right conditions. Less than 25 million years separated those early shoreline lizards from the largest representatives that later ruled every major ocean basin. In geological time, that interval is remarkably brief. During those millions of years, nearly every important part of their biology changed. Limbs reshaped into powerful paddles. The tail became the primary engine of movement. Reproduction shifted completely into the water through live birth. Breathing remained tied to the atmosphere, yet every aspect of diving behavior adapted to a marine existence. Sensory systems, feeding mechanics, and body proportions all changed together as natural selection continually refined each generation. The distance between those predators and familiar living reptiles is smaller than appearances suggest. Mosasaurs belong to the same broad evolutionary group as monitor lizards and garden snakes. Their ancestry remained firmly rooted among squamates, making the journey from a terrestrial reptile to a marine giant something preserved in successive layers of rock rather than confined to imagination. The transformation can be followed through anatomy, revealing intermediate forms that document each major step instead of leaving unexplained gaps. This pattern has unfolded more than once. Ichthyosaurs entered the sea long before mosasaurs and developed streamlined bodies that resembled fish through convergent evolution. Millions of years later, whales began a comparable transition from hoofed land mammals, gradually exchanging running legs for flippers and tail flukes while retaining their mammalian heritage. In the modern world, the Galapagos marine iguana represents a far smaller expression of the same recurring theme. It still spends much of its life on land, yet it already feeds beneath the surface, demonstrating that shorelines remain places where evolutionary pathways can begin. Repeated examples across unrelated groups reveal a broader principle. Whenever productive oceans offered ecological opportunities and a flexible body plan encountered those opportunities, land vertebrates repeatedly entered marine environments and changed in ways that would have seemed improbable before the evidence accumulated. The timescale measured tens of millions of years rather than hundreds of millions, swift by geological standards, though still far beyond the span of any individual lineage's memory. These observations invite reflection without demanding certainty. Evolution does not follow a predetermined destination, and no future outcome can be read directly from the past. Even so, the fossil record shows that life's capacity for reinvention reaches farther than intuition often expects. Given enough generations, changing environments, and ecological openings, familiar creatures may travel astonishing evolutionary distances while remaining connected to their ancestors through an unbroken chain of inheritance. The Cretaceous Ocean offered one enduring answer. It demonstrated that ordinary terrestrial reptiles could become rulers of an entire planet's seas, then disappear, leaving stone to preserve both the transformation and the memory of what evolution once accomplished. Some spans of time become so immense that the human mind loses its natural ability to picture them. 66 million years belongs to that category. The phrase is spoken with ease, yet its true scale slips beyond ordinary experience. It stretches across a duration so immense that familiar measures of history begin to dissolve, leaving only the patient record preserved inside stone. Modern humans have existed for approximately 300,000 years. That alone seems almost unimaginably long when viewed through the lens of individual lives, civilizations, and generations. Even so, it occupies only a tiny fraction of the interval separating the present from the disappearance of the mosasaurs. Their reign as dominant marine predators extended across roughly 25 million years, a period so much longer than recorded human existence that comparing the two almost feels like placing a single grain of sand beside an entire shoreline. Written language shortens the scale even further. From the earliest surviving written records to the present day lies roughly 5,000 years. That span represents only about 0.02% of the time during which mosasaurs occupied the highest position in marine ecosystems. Every empire, every voyage across unfamiliar seas, every scientific discovery, and every story humanity has preserved belongs to an interval that scarcely registers beside the lifespan of those remarkable reptiles. Despite this extraordinary depth of time, our understanding of that vanished world is not built upon distant speculation. It comes from evidence that can be held, measured, photographed, scanned, and studied repeatedly by researchers across many nations. Museums preserve jaws bearing worn teeth, vertebrae marked by healed injuries, stomach contents turned to stone, and skeletons resting in positions that still reveal how muscles once pulled against bone. Each specimen contributes another sentence to a history written without ink. The tooth embedded within the neck vertebra of a flying reptile remains one of the clearest examples. It is a tangible object resting inside a collection available for examination with modern techniques. The shape of the tooth, its microscopic surface features, and the surrounding bone allow paleontologists to identify the predator responsible with remarkable confidence. One instant of predation from roughly 80 million years ago survived every passing age, waiting until another intelligent species learned how to read its message. That ability is among the most extraordinary achievements of science itself. Fossils do not speak with voices, yet they preserve sequences of events through fractures, growth rings, chemical signatures, healed wounds, and patterns of burial. Layer after layer, they provide evidence that different investigators can examine independently, testing one another's conclusions against the same physical record. Knowledge grows through accumulation rather than imagination. The Cretaceous Ocean, therefore, remains close in an unexpected way. Its creatures vanished long before humanity appeared, yet their lives still leave measurable traces scattered across multiple continents. Every conclusion shared throughout this journey began as a fragment of rock shaped by an ocean that no longer exists. Those fragments continue to remind us that even the deepest reaches of Earth's past can remain astonishingly clear when time chooses to preserve its evidence. Absence can leave a deeper imprint than presence. In the rocks formed after the close of the Cretaceous world, the missing predators speak almost as clearly as the creatures that remain. Their disappearance marks more than the end of impressive animals. It marks the collapse of an ecological design whose complexity required tens of millions of years to assemble and has never returned in quite the same form. That vanished design depended upon constant interaction among predators occupying every layer of the environment. Large hunters pursued prey near the surface. Others searched the open sea. Still others entered coastal waters and freshwater systems. Flying reptiles crossed overhead, while marine reptiles waited below. Encounters between dominant hunters were woven into ordinary life, with competition, scavenging, and direct predation linking together species that occupied neighboring positions. Few places existed where an animal could move without entering the awareness of another hunter adapted to exploit that passage. Paleontologists often describe these marine ecosystems as possessing an ecological density unlike anything observed today. The difference extends beyond the number of species or the size of individual predators. It reflects how completely available opportunities had been occupied. Boundaries between shoreline and open water, between river mouths and inland channels, between shallow shelves and deeper seas, all supported highly specialized animals shaped by countless generations of competition. Each successful adaptation encouraged another, producing an intricate network that left little unused space within the food web. Modern oceans present a contrasting architecture. Large sharks patrol extensive territories, toothed whales dive into profound depths, and smaller predators dominate coastal habitats, yet noticeable separation exists between these roles. Empty spaces remain between ecological levels, reducing direct overlap among the largest hunters. Evolution rebuilt marine life after catastrophe using surviving lineages, creating systems that function remarkably well while following pathways different from those that once supported mosasaurs, giant flying reptiles, and their contemporaries. Recognizing that distinction can subtly reshape the way a shoreline is viewed. Waves continue their familiar rhythm. Tides rise and retreat with dependable regularity, and currents carry nutrients across the globe as they always have. The setting appears comfortably familiar because the ocean itself endured. Its physical basin remained, even while its living communities were dismantled and assembled anew across immense spans of geological time. The continuity extends even further. Water itself has circulated through Earth's oceans for billions of years, passing repeatedly through clouds, rivers, glaciers, living cells, and countless marine creatures. Some molecules within today's sea almost certainly moved through the body of a mosasaur before returning to evaporation, rainfall, and circulation once more. The chemistry persisted while the inhabitants changed completely. That enduring cycle offers a rare connection between worlds separated by 66 million years. Looking across today's horizon, therefore, reveals two histories at once. One belongs to the thriving ocean before us, shaped by whales, sharks, fish, coral reefs, and innumerable smaller forms of life. The other survives only through fossils preserved inside stone, recording an ecosystem whose structure has no exact modern counterpart. The creatures disappeared, yet the basin that carried them continues its endless motion, holding memories that only the rocks have learned to preserve. A fossil can reveal astonishing precision, yet every discovery also marks the edge of what can be known. Beyond that edge, the rocks become more restrained. They preserve evidence, not certainty. The closing chapters of the Cretaceous Ocean leave one such boundary, inviting careful reflection while refusing to cross into conclusions unsupported by the record. Across Earth's history, every great extinction has eventually been followed by recovery. Forests returned after devastation, coral reefs formed again, predators rose, prey diversified, and food webs regained complexity. Life repeatedly transformed hardship into opportunity through countless generations of adaptation. Even the greatest biological disasters never erased evolution itself. They altered its direction, leaving survivors to become the starting material for worlds that had never existed before. Those renewed worlds never recreated the ones they replaced. Each recovery unfolded according to the species that remained alive, the climates that followed, the geography of the continents, and the ecological opportunities waiting to be filled. Familiar patterns emerged, yet the participants differed. Similar roles appeared, while the organisms performing them belonged to entirely different branches of life's history. Evolution moved forward without retracing its earlier path. The Cretaceous Ocean followed that same principle. It did not restore an older marine ecosystem. Instead, it emerged from circumstances unique to its own age. Earlier extinctions had removed formidable competitors. Continental flooding reshaped coastlines into broad inland seas. Periodic oxygen depleted intervals altered marine communities, opening ecological space for adaptable survivors. From those conditions arose an interconnected network of predators, unlike anything preserved before, demonstrating how profoundly changing circumstances can redirect the course of evolution. That history naturally leads toward a broader thought, although the fossil record itself remains carefully restrained. If conditions sharing certain physical characteristics were to develop again, including warmer oceans, rising seas, shifting oxygen distributions, and changing predator communities, paleontology cannot specify the exact outcome. Fossils preserve what happened under one combination of circumstances. They do not provide a script for every future possibility, nor do they promise that evolution repeats earlier achievements in identical form. What they do provide is a demonstration of potential. They show that life responds creatively to opportunity, producing solutions that would have seemed impossible before they appeared. Marine reptiles entered the sea more than once through separate evolutionary journeys. Whales later followed an entirely different route from land back into the ocean. Similar ecological destinations emerged from remarkably different biological beginnings, illustrating that evolution possesses many pathways toward complexity without relying upon a single blueprint. The Cretaceous Ocean, therefore, remains both a completed chapter and an unanswered thought. Its rocks preserve an ecosystem reconstructed through teeth, skeletons, chemical signatures, healed injuries, and countless fragments gathered across the globe. They reveal one extraordinary outcome with remarkable clarity, showing what Earth's oceans achieved under one particular arrangement of physical and biological conditions. Beyond that evidence, the stones grow still. They offer no certainty about worlds that never came to pass. They leave us with a record of one magnificent experiment described in remarkable forensic detail, while every other possible experiment remains unwritten. In that balance between evidence and restraint, the fossil record reveals one of its greatest strengths. It tells us exactly what it knows, and with equal honesty, it preserves the space where knowledge has not yet reached. Looking across everything the rocks have preserved, a single picture settles into focus. The Cretaceous Ocean was never a collection of spectacular creatures sharing the same water by coincidence. It was a complete living system, assembled through physical conditions that can be measured, reconstructed, and understood. Exceptional warmth, flooded continents, abundant shallow seas, ecological vacancies, and remarkably adaptable evolutionary lineages combined over millions of years until the ocean reached a form unlike any before or since. Within that setting, evolution unfolded with extraordinary speed. A lineage of land-dwelling lizards entered the sea and, within roughly 25 million years, transformed into globally dominant marine predators. Every major body system changed together, including movement, reproduction, respiration, sensory abilities, and overall size. Other predators evolved beside them instead of replacing them, producing overlapping layers of predation that stretched from coastal marshes to offshore waters, from river channels to the open sky above the waves. Every environment connected naturally to the next through animals capable of crossing boundaries that had once provided escape. None of those conclusions rests upon imagination. Each one emerged from physical evidence collected across many continents. A tooth remains lodged inside the vertebra of a flying reptile. The outline of unborn young rests within the body cavity of a marine reptile that never completed its final pregnancy. Fossil fish preserve the remains of sharks inside their stomachs. Sea turtles carried the marks of repeated attacks while continuing to live for many decades afterward. Every specimen contributes one fragment of a larger reconstruction until individual discoveries become a coherent ecological portrait. The ending of that world arrived from outside its own food web. No faster swimmer, stronger hunter, or more successful predator replaced its rulers. An asteroid struck Earth. Sunlight faded beneath airborne debris. Photosynthesis declined across land and sea, and the smallest producers supporting marine life failed first. Energy vanished from the base of the ecosystem before absence reached its largest inhabitants. Apex predators disappeared because every level beneath them had already begun to collapse. Recovery followed, although it unfolded with remarkable patience. Surviving organisms diversified, ecosystems regained complexity, and new giants eventually entered the oceans through completely different evolutionary histories. Those communities became successful in their own right, though their architecture differed from the one that had vanished. Empty spaces remained where the earlier ocean had maintained continuous connections among its largest predators. The modern sea, therefore, represents renewal, though never duplication. One element alone has endured throughout every transformation. The water itself continued its endless circulation around the planet. Molecules passing through marine reptiles, fishes, shell-bearing animals, and drifting plankton remained part of Earth's hydrological cycle, carried through clouds, rivers, glaciers, rainfall, and returning tides across unimaginable spans of time. The creatures that once filled the Cretaceous ocean have disappeared, yet the physical principles that assembled their world remain part of nature. Temperature, sea level, atmospheric carbon dioxide, oxygen distribution, and evolutionary opportunity are measurable variables, operating according to the same natural laws today as they did then. The Cretaceous ocean stands as the fullest demonstration Earth has yet provided of what those variables can build when they align. It answered that possibility once with remarkable clarity. The record preserves the answer. Everything beyond it belongs to time.